So here we're trying to find the arc length function for the curve. This is a curve, and then with the starting point of 0, 1. So what's the arc length function, and what are we trying to do here? Let's just kind of get this out of the way. What is the arc length? What is the arc length function? What are we trying to do? So let me draw out a graph, and let's say that this is the y-axis and this was the x-axis. And let's say that we had some function f of x, right? And I don't know how it's going to look. It's like something like this, right? I don't know. This is some arbitrary function. It's going to go all the way to the left, all the way to the right. And let's say that I wanted to find the area, or rather not the area, the arc length, right, of this function from a to b. That is basically this arc length here. We wanted to find this, the length of this, this thing here, this arc, a lot of these arcs here. So we want to find the length of this here. So if we were to kind of put this and kind of stretch it out like a string, what would be the length of this string? That's what we're trying to find, the length of this string. So in order to find the arc length, given the a to b, right, given the length, we would have to use a formula. This is the arc length formula. So let me call this L equals integral from a to b. If this function is f of x, then the arc length, it would be the root of 1 plus f prime of x quantity squared dx. This is the arc length. But here we are given an a and b. In this problem, we're only given the starting point, so we're only given a. We're not given b. So we have to kind of write a function. That's why it's a function, because we're plugging in of what's a function. A function is something that accepts an input and outputs an output. In this case, we're only given the starting point, so guess what would be the input? The ending point. And so the ending point, which is the b value, would be the input into the function, and the output would be, of course, the arc length. This is an arc length function. So let's write it as a function. This is going to be L of t, and t is going to be the input. And the reason why I didn't choose x, L of x, because x is already representative of the values that you plug into the derivative or the function. So I'd rather just use something else that represents the upper bound of integration, which is, in this case, t. You can also use z or something else. And then a would be the lower bound. And then this is going to be the root of 1 plus f prime of x squared dx. This is an arc length function. And this is just a kind of a template, I guess you could say, for an arc length function. Now let's write the arc length function for this function here specifically. So the function here that we're looking at is sine inverse of x plus the square root of 1 minus x squared. You need to know that the derivative of this function. And in order to find the derivative, we need to know what the derivative of sine inverse of x is going to be. And that's actually just going to be 1 over root 1 minus x squared. You need to know this. Plus, if you forgot this, go review the derivatives, trigonometric inverse derivatives. This is going to be plus 1/2 times 1 minus x squared raised to negative 1/2 times the derivative of the inside, which is just negative 2x. Right? This will cancel with this, and we will end up with y prime is equal to 1 over square root 1 minus x squared plus, minus, because we have a negative, minus, and then this is just going to be x over square root of 1 minus x squared. Here we can actually combine these. So y prime is just equal to 1 minus x over root 1 minus x squared. And that's our derivative. So let's use this template to write the function. L of t is equal to integral t a, right? A actually is given to us. It's the starting point. And in this case, we're looking at x's, so we're looking at the x value of the starting point. If we were looking at y's, if it was like g of y, then we would look at 1. But we're looking at 0 in this case. And then that's the square root of 1 plus f prime of x. This is f prime of x, which is y prime squared. So what's 1 minus x? Let's write this here. What is y prime squared? What is the square? If we square both sides, what is that equal to? Well, so y prime is just going to be, y prime squared is just going to be equal to, so the squaring the top and the bottom, so squaring the top is 1 minus x quantity squared over the root 1 minus x squared is just 1 minus x squared. What's this 1 minus x squared going to be? So let's expand this. 1 minus x times 1 minus x, that's just 1 minus x plus x squared, which is equal to 1 minus 2x plus x squared. X squared minus 2x plus 1 over 1 minus x squared. That's it. So this is what I'll include over here. This is just going to be 1 plus x squared minus 2x plus 1 all over 1 minus x squared. Okay, dx. So someone plugs in into this function the upper bound of integration that goes up here, that will be evaluated, and you'll get a result. So this is the arc length function. This is it right over here. It's a function that needs an input that produces the output for the arc length. Now, another thing that I wanted to point out is if someone wanted to find, say, the derivative of the arc length function, so let's say someone wants to say, what would be the slope at 5 of the arc length function, or something like that? What would we do? How would we do this? Well, that would just be, we would find the derivative of the arc length function, right? So that's just L prime of t. This would be equal to the derivative of this whole thing. And remember, this comes back to FTC part 1, which is the fundamental theorem of calculus part 1. The derivative of this would just be equal to root, we just get rid of this integral and this dx, whatever. We just get replace all the x's with t's. So that would just be 1 plus t squared, and I'm going to write my t's a little differently to make sure that I don't get confused with the plus signs. T squared minus 2t plus 1 all over 1 minus t squared. And then this is going to be your derivative. So if someone wanted to find the slope at 5 of the arc length function, we just plug in 5. This is another thing I just wanted to point out here. All right, so that was this video. I hope you found this video helpful.